Hello.
Yes, sir. Yes,
Okay.
sir.
So I think we should start. So yesterday we were talking about the unsteady discretization. So it was kind of spatial temporal discretization. So today we are going to talk about a bit detail about it. So starting as of now. So let us consider the heat conduction equation. So later on we will also go for unsteady conduction with convective transport. But today we are going to talk about one-dimensional. So it's a kind of recapitulation, a part of which I derived in the previous class. So one-dimensional unsteady heat conduction equation. Heat conduction equation. So the equation looks like rho Cp. So Cp is basically the specific heat capacity. Rho Cp dT equals to ddx of k dt dx plus S. Right? S is basically your source term, and this one is a diffusion term, second one. The first term on the right hand side of the equation. The first term on the left hand side of the equation, that is basically the temporal term. So which actually at a specific point itself, it gives you the time evolution of the temperature. So temporal term. So T itself is a function of X and T in case of this case, since this one is a 1D case. But if it's a 3D case, then that's a function of X, Y, Z and then T. So spatial coordinates along with the time itself. So So how we are going to discretize it? So initially what we used to do is that first we used to integrate it with the volume itself, and then what we what we used to do is that then we used to use a Gauss divergence theorem, convert that volume integral into area integral, and then we used to carry out this area integral at the cell faces, and from there we used to discretize the whole equation. That's the way we used to do it. So today what we are going to do is that we are going to do both time integration and the volume integration. So this one is T to T plus delta T, and this one is for the control volume. So if I draw it again, our control volumes looks like this. So capital P is basically the control volume of our interest, and capital E is the east control volume, and capital W is the west control volume. And small w is basically the cell phase between the capital P and the capital W control volume, and small e is the cell phase between the capital P and the capital E control volume. Okay, so it is clear to all of you. Sweta Arpan.
Yes.
Okay, so if I go it like that, so rho Cp dt multiplied by dV into dt prime. So the differential time element I'm using dt prime, you can use dt, both mean the same. So this is equal to T to T plus delta T, and then there is a control volume, and then there is a ddx of k dt dx into dv into dt prime plus s of dv into dt prime, control volume, and then T to T plus delta T. Is it clear to all of you? Then what we are going to do is that if I go to the first integral itself, which is the temporal integral CVT, and then this T to T plus delta T. So rho C dt and then this dt prime. So this will come as rho C T at T plus delta T minus of T at T multiplied by uh, delta V. Delta V. Okay. Is it clear to all of you? So this one is come as rho Cp delta V T T at T plus delta T minus of T P at T. So this temperature at the control volume of interest. So which is basically my P control volume, and the spatial discretization we will do at the right hand side of the equation. So for the right hand side of the equation, the first term is basically T to T plus delta T. So which is basically K dt dx E minus of, since I have converted that volume integral into a area integral, and Ka dt dx at small w multiplied by dt prime is equal to Ka dt dx. So first, if I resolve this first integral, so it will come as T to T plus delta T Ka. So there is a control volume integral also. So for which I think, yeah, that's already been done. So this is Ka T minus Tp divided by delta x E E. So if I draw the control volume measure, it will be more convenient for you. So this one is P, this one is E. Using the central difference formula, we are finding out the we are basically finding out the discretization of the gradient. So this will be equal to minus of, so this will be E, so it will be K A small w T P minus dw divided by delta x wp, or you can write the delta x to be like this, and then this multiplied by that of delta t. So now if I simplify it further, so it is Ka delta x Pe T to T plus delta T P minus Tp dt prime minus of T to T plus delta T Ka by delta x Wp Tp minus Tw multiplied by delta dt prime. Okay. So now what we are seeing is that we have to find out the time integral of T, Tp, Tp and Tw. Okay. So what we have to do is that we have to define it. How to find out the time integral? So this it, which is basically the integrand, the integration of the variable inside. So this is Tp, T prime, Tt prime. I'm defining it as theta Tp, T plus delta T plus 1 minus theta Tp at T delta T. Okay. So this theta is basically an user defined parameter. Okay. It can be equal to 0, it can be equal to 1, it can be equal to, it can be within 0 and 1. So it remains constant throughout the simulation. So what we are doing is that we are defining the integrand in that manner. So which is basically a function of the that Tp at T plus delta T, which is basically your next time step, the temperature at point T at the next time step, and then it is weighted by theta plus 1 minus theta multiplied by TPT. So TPT is basically your temperature at point P at time T. Okay. So is it clear to all of you?
So I have a doubt like dou t by dou x, that thing you wrote as t minus tp by delta xp. That is okay. But my doubt is, so that means we are assuming that the temperature is varying linearly in the control volume.
Yeah, we are assuming it. So in case of
Assume,
central difference formula, we assume it to be linearly. In case of quick scheme, we assume it to be quadratic. So your
yes, yes.
question be like, if it's a quadratic profile, so why we are assuming it to be a linear one? Okay. So for
Uh,
example, if your profile is somewhat like this, so if I zoom it further, I can approximate this curve as piecewise
as
linear
a straight
functions.
line. Yes, yes.
So that's why you can use a central difference formula. But if I
Mhm.
actually take the cell size to be like this, and if it's like a curve like this, so for example, if the curve is like this, and then I'm actually taking a grid like this, and then I'm assuming that this is linear. So this is my error. So either you assume the profile to be quadratic or a polynomial one, or you reduce the cell size. That's why I always say that if it's a curvy thing or in the near wall region where we have a parabolic profile for a laminar flow through a pipe itself, you actually use a wall function or you use a higher accurate discretization scheme or you reduce the cell size and then you can use a low order discretization scheme. So many things can be done, but we take that thing into account. Okay, is it clear to you?
Yes, sir.
These assumptions you will see, for example, when you are doing the simulation, uh, and after doing the simulation, if you don't see the results to be an accurate one, then you will kind of reverse engineer and you will see that what are the possible reasons for it. Either the discretization scheme is wrong or either the cell size is wrong. That way, and if you actually do multiple simulations over the period of time, you will understand that what are the errors that can come into play. Okay, so that I will discuss with you at the later part itself. For example, let us, for example, there is a parabolic profile like this. Okay, let us draw it in a much more. Then I actually use a first order scheme and then I assume the profile to be a linear one and the cell size is force. So what are the things which will appear to be inaccurate? So what do you think, Arpan? What are the things which can appear to be inaccurate?
The velocity.
The velocity, the pressure, the mass flow rate, these are the things which will come in to be inaccurate. So what you will do is basically first you will see the contour here. So there will be some problem with the contour itself. So if I actually plot the profile in my CFD solver, then I will see that it is not coming to be parabolic, it is coming to be linear. Then I will understand that some issues are there. I will find out the stress. It is not tallying with the numerical, the analytical solution itself for a flow through a pipe. Then I will understand that the stress itself is inaccurate. So I will see that where the areas lie, the first order variable or the second order variables, the gradient itself. I will also see the mass flow rate in the domain. I will also see the divergence in the domain. So whether continuity is maintained or not. So these things I will look into. So I will kind of, that's why it is essential that you know that what do you mean by divergence, what do you mean by curl. So for example, that is not an rotational flow, it's an irrotational flow. Okay. But on the other hand, you will find the curl to be a finite one. Okay. So what do you mean by that? That means a simulation itself is kind of inaccurate. For irrotational flow, if you are actually getting this curl to be not equal to zero, then it is inaccurate.
Yes, sir.
So those are numerical inaccuracies which can come into play. So I think that's how you actually come to know that what are the problems which are present in the simulation. But if the cell size is small, we can assume the profile to be a linear one. Okay. Uh, Others, do you have any issues, Sweta? Sweta, okay. Yes. Do you have any problem or do you have any kind of doubts you have? Hello, Sweta. Okay. So now I'm going to discuss about uh, that how we are going to reduce the whole equation itself. So, uh, so now this IT is basically equal to T to T plus delta T. By the way, Sweta, I got your mail. I will solve the problem and get back to you. I didn't get time this week, but I hope the previous week itself I was busy. So I hope this week I will be able to do it. So this Tp t prime dt is basically equal to theta Tp plus 1 minus theta Tp naught and then multiplied by delta t, where theta is a wave factor, which is user defined. So you can make it to be a dynamic one. Uh, you can make it to be a constant. As of now, you assume it to be a constant. Okay. So if theta equal to 0, we give full weightage to Tp equal to Tp naught. So you actually put theta equal to 0, then this term becomes 0, the first term, and the second term actually becomes Tp naught. And if theta equal to 1, we give full weightage to Tp at t plus delta t equal to Tp. And if theta lying between 0 and 1, okay, we give non-zero weightage to both. So now we will talk about how to discretize the source term itself. So T to T plus delta T, and then there is a control volume. Then this is S dV dt prime, and then this is T to T plus delta T, and this is var del V dt prime. So as of now, we are assuming the S to be a constant one. So S can also be written as S equal to SPTP. So as I have already said, so let us consider it to be somewhat like this. So if it is constant, then A is equal to SP, otherwise it is A is equal to AC plus SPTP. So SPTP actually takes into account the linear variation of the source term with the temperature profile, whereas linear variation of the source term, and first one is a constant term, and second one is a linear variation of source term with temperature. So another thing should be kept into account that if you want it to be numerically stable, SP should be negative. So which actually satisfies the Scott-Barrow criteria, and which actually makes a matrix to be a dominant one, diagonally dominant. So which is actually one of the criteria which is required when you are going to solve the matrix equation of X equal to P by using methods like Gauss-Seidel method, indirect methods like that, and then it is required, and that's why SP is actually desired to be a negative one. So which I will come to the later part of the course itself. So this equal to T to T plus delta T, and this area, this is delta X into dt. Okay. So area multiplied by T to T plus delta T, SU plus SPTP, and this T prime, and then this is dt prime. Okay. So this typically we can reduce it to like A SU delta T plus S ASP T to T plus delta T TP T prime dt prime, and then we can write it to be like ASU delta T plus ASP delta T theta TP plus 1 minus theta TP naught. Okay. Is it clear to all of you? Hello, am I audible?
Yes, yes,
Shweta,
okay.
Arpan. Okay. So now I'm going to discretize the whole equation itself. So this is rho Cp Tp minus Tp naught delta V equal to theta KEA T minus Tp divided by delta X P minus KWA Tp minus Tw divided by delta X WP multiplied by delta T, plus 1 minus theta. This you can easily do. So KEA TE naught minus TP naught divided by delta X E minus of KW A TP naught minus TW naught delta X WP multiplied by delta P plus A SU delta T plus SP theta TP plus 1 minus theta TP naught delta T multiplied by P. Okay, is it clear to all of you?
Yes, sir.
So one thing you may ask that initially I said it to be like A's delta V equal to ASU plus SPTP, but now all of a sudden uh, I'm calling it to be like A's delta X is equal to AC plus SPTP. I have no problem with both of them, but in the books itself I saw that they are actually treating it in this manner. So one of the possible reason is that by assuming A's delta X equal to AC plus SPTP, I can divide the both the sides by A delta T. Okay. That's why, for the sake of simplicity or mathematical convenience, they are assuming that A's delta x equal to AC plus SPDP. But it depends upon you how we make this thing to be in your code itself. So we write the equation so that it is convenient for us to code. Okay. So that's why from the very beginning, you can see that I'm trying to generalize the whole thing. So when I told you in one of the classes like APTP equals to AETE plus AWTW plus source term. Okay. So these coefficients will change. This AP, AE, and AW will change when I actually change the discretization scheme. Okay, so this one is kind of one-dimensional problem, where P is a central control volume of my interest, this one is a east, and this one is a W, the west control volume. Okay, so now instead of that, if it's a two-dimensional one, okay, so how do I write it? So if it's a two-dimensional one, so this becomes north, this becomes south. So now this will be equal to ANTN plus ASTS. So if it's a three-dimensional bond, this is top, this is bottom. So this becomes ATTT plus ABTB. So it's like a superimposition principle. So these coefficients will change if I change the discretization scheme. If I actually change the dimensionality of the problem itself, so instead of this AE, P and AWTW, ANT and ASTS, and also ATTT and ABTTB. So this will come into play. So N is north, S is south, E is east, W is west, P is top, and B is bottom. Okay. So this is your X direction, this is your Y direction, and this is your Z direction. Okay. So this is one of the things you should take into account. So whenever you are actually writing the equation, it should be convenient from the point of coding. If you can't generalize it, it will be very difficult for you to code. Is it clear to all of you?
Yes, sir.
Okay. In the next class, I think I will go back to coding again. So then I will discuss about how to do coding for other problems. Okay.
So I was watching another lecture, sir, in that this stability criteria was discussed, like the coefficients AE, AW, AN, AS, they all should be of the same sign, something like that. Is that thing called as Scarborough criteria or what?
No, this is not the Scalabaro criteria. This is called kind of transport illness. Okay. So
Boundedness.
no, it is transport illness. Boundedness is you have the temperature within the two boundaries. That is called
Yes, sir.
boundedness. So this is called transport illness. Scarborough criteria I will discuss. So this actually increases the diagonal dominance of your matrix. So when you are going to solve this equation, that is ASU delta T. So ASU delta T will basically tend to appear in the right hand side of the equation, and this SP delta T will basically go to the left hand side of the equation itself. Okay. So if SP itself is negative, okay, so if it actually goes to the left hand side of the equation, then it becomes positive. Okay,
Yes, sir. SP should be negative. It comes from this thing only that the
no,
coefficient
no,
should be positive, something
no,
like
no.
that. No?
Let me speak. SP is negative at the right hand side of the equation. I said that when you're writing the source term as AC plus SPTP, SP should be negative. Okay, you agree with me? Okay.
Yes.
So on the right hand side of the equation, this SP is there. So when I'm actually writing this AX equal to B format or AT equals to this B format, then T is basically what? A inverse B. So this, if I actually write this T itself, so at the column matrix itself, it will be like T1, T2 and going to Tn. So this is my P, maybe 1, 2 and whatever you call it to be. Okay. So if
Yes.
theta, हाँ please,
No, sir. Go on, sir.
हाँ इसके बाद क्या होगा ये जो TP जो है this theta TP is positive, TP is positive, theta itself is positive. For example, theta equals to 1 मैंने पकड़ लिया है, ठीक है. इसके बाद SP नेगेटिव होगा तो वो बेसिकली क्या होगा तुम्हारा TP का कोएफिशिएंट बनेगा and it will come to the left hand side of the equation, it will become positive because it is minus SP then. The positive part will actually add to the diagonal part of the matrix itself because this TP coefficients actually lie here.
Yes, sir. Okay.
So it will increase the diagonal dominance of your matrix. And this is called the Scarborough criteria. And that's why I told that SP should be negative. If SP is positive, then it will actually reduce the diagonal dominance. And if it actually reduces the diagonal dominance, it becomes difficult for Gauss-Seidel method to converge. Okay,
Yes, sir.
that's a so when the coefficient that should be positive, that is basically the transportiveness itself. So those things are kind of good kind of approach. There is another method which is called the von Neumann stability analysis that I will also discuss in the class. So by that method, you can accurately find out that whether the numerical scheme is positive or not, it is stable or not. That is the I think that is most kind of scientific method because transportiveness will not always give you the correct answer. In case of temporal discretization itself, the spatio-temporal discretization, transportiveness will not always give you the correct answer. Okay, so then you actually go to von Neumann stability analysis, which I will discuss in the later part of it. So as of now, so I hope I am. So you are kind of satisfied, right? The question you asked, I'm able to
Yes,
answer
yes.
it, right? So this rho Cp delta H by delta T, I'm rearranging the equation that I've written in the previous slide. So Ke delta H Pe and this theta plus Kw theta delta X Pw minus of S P theta, sorry, S P theta and this Tp. Now you can see that if Sp is negative, then it is coming to be positive, and the coefficients of Tp actually lies along the diagonal. So Ke
Hmm.
delta X Pe multiplied by theta P, because the small things are very much important. The small intuitions you build up is very much important when you write your own code. It becomes easy for you to decompose a whole problem into small parts and then you find the solution of it. Otherwise, it becomes a mess. And this plus of rho Cp delta x by delta t minus of Ke delta x p plus of Kw delta x wp minus of Sp 1 minus theta dp naught plus s. Sorry. Then we can go to again like APTP. equal to AW multiplied by theta TW 1 minus theta TW naught. So I am again going to the coefficient format from the point of view of coding. Plus 1 minus theta TE naught. AP naught TP naught AC. Then group AP is basically, if I tally with this equation, the equation which is written up, so AP equals to rho Cp delta x by delta t plus 1 minus plus theta AE plus AW minus SP, and this equation, and AP naught prime equals to, or AP naught equals to, not prime, okay, rho Cp delta x by delta t minus AE plus AW minus SP 1 minus theta, and then this AW equals to KW by delta x, oof, WP, E equals to KE by delta x, E. Okay, is it clear to you?
And what about 1 minus theta t naught? Those things.
Uh, 1 minus theta
Then
T.
1 minus theta tw naught is there.
That you can do it. That's not a problem. So TP is given, AP naught is given, E is given. That's not a problem. I've written the coefficient to be an accurate one. So AWA is written, AP is written, and AP naught is written. So then you put the coefficient in the equation, you get the whole equation. That's what I'm saying. Is it clear to you?
Yes, yes, yes.
Mhm. Okay. So now what we are going to do is that we are going to consider a special case. Let's consider a special. So theta equals to 0, which is called the explicit scheme. Okay. Then this t to t plus delta t is basically equal to tp t prime dt is equal to tp not delta t. Okay. Since I've written the equation as t to t plus delta t tp prime, and this tp of t prime dt is basically equal to theta tp plus 1 minus theta tp naught delta t. Is it clear to it?
Yes, sir.
Okay. And then what you have to do is that the whole reduced equation looks like this. So rho Cp delta x by delta t Tp is basically equal to kW delta x Wp Pw naught plus Ke delta x Pe Te naught plus rho Cp delta x by delta t minus Kw by delta x plus Ke by delta x Pe minus Sp Tp naught plus. Okay. So this can be further written as APTP equals to AWTW naught. Now the coefficients remain the same, only the theta changes is TW naught and TE naught. So as you can see at the right hand side of the equation, we are basically getting it at our previous time step. So you actually these are if you iterate it for a single time step, so this actually becomes your initial condition. And the left hand side of the equation actually gives you the temperature at the next time step. So this corresponds to not making a matrix kind of an equation. You can directly get it from the equation itself. Okay, so you can directly put out the values and then you can find out the value of the temperature here. So you don't have to form a matrix. So it's a kind of inexpensive in nature, but the problem is that it has some stability issues, which I'm going to be discussing in this class. So this AP is basically equal to rho C delta X by delta T, and this AW plus AE plus AP naught minus of SP. Okay. So then going to the equation itself. So AW plus AE plus AP naught. So this AW plus AE plus rho C delta X by delta T minus of AE plus AW minus SP 1 minus theta. So this is AW plus AE plus rho CP. Let me, I think this is not required. This will be solved for this. There's no point of this. So as I've talked earlier, so if theta equals to 0, that is basically called a explicit scheme. So if theta is basically 0 and 1, that is called an implicit scheme. So if theta equals to 1, that is called fully implicit. So in case of fully implicit scheme and implicit scheme, one thing you can see is that you basically have to form a matrix. So that's a pain, but that is much more kind of, what should I say? That is much more kind of numerically stable. So going to the equation itself, so one of the thing you will see is that AW is that if I go to the transport in this kind of thing, so it is AW is KW by delta XWP, and A is basically equal to KE by delta XPE, and EP naught is basically equal to rho C delta X by delta T minus of KW by delta X WP plus of KE by delta X PE minus SP. EP is basically equal to rho C delta X by delta T. So one of the things we can see that AW is positive, AE is positive, AP is positive. But there is a condition you have to obey in order to make it to be positive. For example, we are assuming that SP equal to 0. Okay, for the time. So AP naught if it's to be positive, then rho CP the delta X by delta T. So let's put a this okay, minus of 2K if KW equals to KE. So we are assuming uniform conductivity over the whole rod itself. So this is positive. So rho Cp delta X by delta T is greater than 2K delta X. So delta X is squared. So delta T should be less than rho Cp delta X squared by 2K. So there is a constraint on the time scale and the spatial discretization itself, the cell length itself. So delta t and delta x are bound by a condition to obey transfer. Trans. So if this is not obeyed, then transport fails, and then you basically get to see numerical oscillation. So which you have seen in case of the appoint scheme itself. So I think those are the things you should take into account. Okay. So is it clear to you? And even if SP is there, then SP actually comes at, so it changes a bit. If SP is there, then the condition becomes rho Cp delta is by delta T plus of SP is greater than 2k by delta x, and minus of SP is positive. So then you get to the other side of the equation and then you solve it. So delta x by delta T is greater than 2k by delta x minus of SP, which is positive. So now delta x or delta T should be less than rho Cp delta x 2k delta x minus of s. So it changes a bit, but in the books itself, this you will obviously find out. So this is the criteria for the stability itself. So is it clear to all of you? Hello, am I audible?
Yes, sir, it's clear.
Okay. So now I will show you how to find do the discretization at the spatio-temporal discretization over a bunch of cells. So we are going to the previous problem itself. So there are five cells: one, two, three, 4, and 5. Okay, so this is 1, this is second control volume, this is third control volume, this is fourth, and this is fifth control volume. So this is TB and this is TA. So T and TB are basically your the value of the temperature at the boundaries at point A and point P itself. So now what we are going to do is that first I will go to the first cell, so which is this cell itself, and this is 2, this is P, and this is W. Okay, so let me write out the equation. So this comes to be rho Cp Tp minus Tp naught delta V equals to T to T plus delta T Ka dt dx at east minus of Ka dt dx at W dt. Okay, so this has no source term, by the way. So this is the same linear heat conduction itself. Since you know that this actually becomes a steady problem, so you will get the same solution over the period of iterations itself. But now I'm going to solve it in a spatio-temporal manner, and there is no source in heat dot. Okay, so is it clear to all of you?
Yes.
Hmm. And then going to the problem itself. So this becomes rho C Tp minus Tp naught Tp minus Tp naught A delta x equal to T to T plus delta T K T minus Tp the delta x dt. So which is basically the formulation is there. So now this is at the east itself, and going to the west hand side of the equation. So this is basically, for example, if I actually let us pose a problem somewhat different. For example, TA is basically a zero flux boundary. Let us see how we deal it numerically. So instead of TA, you basically have your dt dx at your west phase equal to 0. Okay. So if instead of TA and TB at the both side of the rod, you actually have a this dt dx at west phase equal to 0. So this boundary condition, the zero gradient one, you can put it directly, and then this becomes dt. Just trying to find some, introduce some variations in the problem. So rho Cp delta is by delta t, Tp equals to k by delta x, Te naught, and then 0 Tw naught plus rho C delta x by delta t minus T of delta x Tp naught. Okay. Otherwise, one thing you can do is that if it's not a zero flux, zero flux means Q is zero, so which basically means minus of Td dx at a certain cell phase is 0, which is your at point equal to 0, which actually means your zero gradient boundary condition. So if actually equal to t equals to ta at this point, you can write this equation to be like this. So it actually becomes t to t plus delta t, and this k t minus tp divided by delta x, and this dt actually lies outside, so you don't have to write it here, minus of k tp minus tw divided by delta x divided by 2. And then if this is dt, so you already know that Te dt is what? Te dt is actually can be written as theta t plus 1 minus theta t naught. Since we are assuming theta to be equal to 0, which is basically your explicit condition. So integration t to t plus delta t, and then this delta t itself. So this theta equal to 0, this actually reduces to be Te naught delta t. Okay, so you can directly put it here and then you can solve it. Okay. So depending upon the problem itself, you can change it. Okay. So is it clear to all of you?
So in the second line itself, we have assumed that you are using explicit scheme, right?
Yeah, we are actually for this problem itself. Let me clarify you further. So we are using explicit spatio-temporal discretization, spatio-temporal discretization, and at one boundary condition, there is basically your zero gradient boundary condition, which means that there is no heat flux, which is the adiabatic boundary condition. And at the other side of the rod itself, you actually have Tb, which is a constant temperature boundary. Is it clear to all of you?
In the no flux condition, dou t by dou x equal to 0. So that means T1 should be equal to Ta. You've written T
Uh,
equal to T. I'm saying why not T1 equal to Ta? Because dou t by dou x is 0, right?
that you can do it. Those kind of things you can do it. But that is the case when you actually have a steady state condition. But if it's a spatio-temporal one, then that will not be equal to T1 is not equal to Ta. But when the solution converges, then T1 basically equals to that of T. This condition you are seeing, right? At the waste phase itself. So this is equal to 0. So if I discretize it, it becomes T1 minus Ta divided by delta x divided by 2 equal to 0.
Yes.
T1 equal to T. Ah, that can be used. That can be used, but I am writing it in a general format. But generally what we do is that we don't discretize a boundary condition. We kind of use it directly, the whole equation itself, and we can directly put the boundary condition to be in the equation. Okay, is it clear to you?
Yes, sir.
Okay. So then going to the note 5 itself. So the cells in node 5, sorry. Node is a different term, you know. So this is east, this is west, and this rho Cp, Cp minus Cp naught, K delta equals to T to T plus delta T, K T to dx at east minus of K T to dx at west, and then you have dt prime. Then how to reduce it further? So basically K using the forward recurrence scheme, delta x divided by 2 and this dt minus dt minus of K delta x dp minus dw multiplied by dt prime. Okay, so 2k k by delta x dv naught minus dp naught multiplied by delta t. Since we are using the explicit scheme method, so I can directly put it the initial value of the value of the temperature at that time step multiplied by delta T minus of K by delta X Tp minus Tp naught minus Tw. So which can be reduced further. So rho Cp Tp minus Tp naught delta X by delta T K by delta X Tv naught minus Tv naught minus K by delta X. So the area you can subtract from both sides so that this K delta X actually this K cancels out from both sides. So this A actually cancels out. You can write it like this. Then this is basically equal to Tp naught minus Tw. Then this will go C. Yeah, that's a form of the equation. Okay. So is it clear to all of you?
Yes.
Okay. So if I write the general form of the equation itself, the general format of the equation. So this is your cell centroids. So 1, 2, 3, 4, and then there is 5. Okay. So AW, AE, AP, then there is SQ, there is SP, there is PP naught. So this is 0, this is K by delta X, K by delta X, 0, this is rho Cp, delta X by delta T, and then this is 0, this is 0, this is 2K delta X dV, this is 0, this is 0, this is minus 2K by delta x and rho c delta x by delta t minus of k by delta x rho c delta x by delta t minus of 2k by delta x and rho c delta x by delta t minus of 3k by delta x. So as you can see, all the terms are basically coming to be positive. ASP is one of the term we want to be negative. So this is also coming to be negative, fortunately. And therefore, these conditions are actually, if I want to make it to be positive, so I will get three conditions. So rho c delta x by delta t is greater than k by delta x. So delta t should be less than rho c delta x square by k. And then there is other terms which is rho c delta x squared by 2k. And then there is another one which is rho c delta x squared by 3. So Arpan, what do you think? Which one is the most strict condition among the three?
The first one, sir. It
The
will
first one.
satisfy all.
Yeah, which
Yes, sir.
satisfies all the conditions. So the first one we will actually obey. So delta t should be less than rho c delta x squared by k. Okay. So if this one is a problem you are facing. So if this one is not obeyed, so in the code itself you have to write that when you are actually choosing delta k and delta t itself, since rho c and k you will actually know at the start of the simulation. So since these are the properties of the material itself that we are dealing with. Okay. But delta x and delta t are the variables. So once delta x you are defining, then delta t is automatically you have to define that should be less than this. So if delta t is less greater than this, you don't have to do the simulation itself. You throw an error. You say that you should take delta t to be less so that this condition is satisfied. Okay. So before doing the simulation itself, you know that whether that is going to be becoming unstable or not. Okay. So this way of approach actually becomes much more handy when you are actually dealing with this kind of thing. Okay. So is it clear to all of you? Hello, am I audible?
Yes, sir, clear.
Clear. So uh, let us uh, go for another thing. I think we can go for another thing also, which is your fully implicit one. So the same problem with a fully implicit one. One, two, three, four, five. Okay. So in the fully implicit equation, we all know that we can make it to be like this. So if I actually solve one equation for you, so which is basically rho c a delta x Tp minus Tp naught equals to t to t plus delta t and this ka dt dx at e minus of ka dt dx at w multiplied by dt prime. And if I actually if I for example if I start with the first cell center, the first cell center is this one, the same boundary condition which is an insulated boundary condition at the left hand side of the domain itself. So rho c uh, a delta x Tp minus Tp naught Ka T minus Tb divided by delta x Dt prime T to T plus delta T. Since this gradient is becoming zero, since at the west face itself the rod is in zero. So this actually becomes Ka delta x T minus Tb multiplied by delta T. Okay. So the whole equation, if I cancel out the area from both the sides, so the whole equation becomes rho Cp delta x delta t. So I'm dividing A delta t, the whole expression by A delta t on both the sides. So this becomes delta x t plus k dt by delta. Okay. So there will be a minus sign. So this plus rho c delta x by delta t, and this is dp naught. So this is equal to rho c delta x by delta t plus k by delta x dp equals to k by delta x t plus rho c delta x by delta t multiplied by t. Is it clear to all of you?
So why did you take that gradient rho t by dou x at western face 0?
Because I said the same boundary condition, the same problem, dt dx equal to 0. The same problem
Okay.
that है वही वाला problem
Oh,
solve कर रहा हूँ ना.
okay. This is point 1 point 2. Okay, sir. No.
हाँ हाँ ठीक है. इसके बाद 5 नंबर वाला देखते हैं. ठीक है. This fourth and fifth point itself. So this one is east, this one is B, this one is small w. So same way you this A rho C delta x Tp minus Tp naught equals to T to T plus delta T equals to dt dx east minus A dt dx west multiplied by dt prime. So now similarly we can write that 2k by delta x Tb minus T2 delta T Ka by delta x Tp minus Tw multiplied by T. Is it clear to all of you? So we can reduce it further. So Tp rho c delta x by delta T plus
So
3k
why
by
there?
हाँ
Sorry,
बोलो.
sir. Sorry for interrupting. So why there is 2 in the above line in the first term of the RHS?
क्यों नहीं होगा
2k,
2. हाँ तो नीचे
2k.
डेल्टा एक्स बाई 2 होगा ना. तो तुम जब टीपी माइनस टीपी करोगे मतलब T5 होगा तो क्या होगा ना. तो यहाँ पर डेल्टा एक्स बाई 2 है ना. We are using the forward difference formula here. This one is a boundary cell centroid.
Yes, sir. Yes, sir.
ये सब चीज दिमाग में रखना पड़ेगा ना. So delta x by delta t, 2k by delta x. बाउंड्री में जब डील करोगे ये सब आएगा. k by delta x tw plus 2k by delta x tb plus a plus rho c delta x by delta t tp naught. Okay, so that's how the whole equation looks like. So now if I go to the same table that I've drawn before, APTP equals to AWTW plus AETE plus AP naught TP naught plus AC. AP naught equals to rho C delta X by delta T. AP is basically equal to AW plus AE plus AP naught minus SP. So if I actually go to the cells and parts, so this one is a cells and parts. This one is AW, this one is AE, this one is AP naught, this one is AC, this one is AP, and this one is 1, this is 2, this is 3, this is 4, and this is 5, and this is 0, this is k by delta x, this is k by delta x, k by delta x, then this is rho C, rho C delta x by delta 0 0 2k Tv by delta x 0 0 2k by delta x. Similarly, rho C delta x by delta t plus k by delta x rho C delta t delta x by delta t plus of 2k by delta x rho C delta x by delta t plus 3k by delta. So do you see any constraint here, Arpan?
Sorry, sir.
Do you see any constraint here? So in case of fully explicit scheme, we were seeing that we have to see some follow some boundary conditions
No, sir.
depending upon. There is no constraint
All
here, right?
already positive. Yes, sir. No constraint.
Already positive, and this one is negative. We want it to be negative. Okay.
SP we want to be negative means other AP, AW, AE, those all are positive.
So this is called unconditionally stable. But this is a bit numerically expensive. But this is numerically expensive than explicit scheme. Since we have to form a matrix. Okay. Is it clear to you?
Yes, sir.
Okay. So after this, we will start another thing which is called the pressure velocity coupling, which is called the simple algorithm. Today I'm going to discuss about what actually what is the concept of staggered and collocated grid. So one is called staggered grid, another one is called collocated grid. Okay. So typically, what is called grid? So grid is basically the control volume which is formed by the intersection of the stances in the x and the y direction. If it's a 2D problem, if it's like a 3D problem, then you have the stances in the z directions also. Okay. That is what we call it to be a grid. So typically, this is called the control volume. So if I consider that to be a 2D one, so if it's a 3D one, it actually becomes a cuboid like this. So cuboid or parallelopipe depending upon the dimension that you choose. So if I'm assuming to be a 2D one, so if I'm solving the equation here, for example, discretizing the equations in the cell centroid, then it is called collocated grid. Okay. For example, instead of solving at the cell centroid, we are basically solving at the cell face. Okay. So then it is called staggered grid. Okay. So for example, if you are solving both the continuity and the momentum equation, continuity and momentum equation in the same cell centroid, then it's called collocated grid. But if I'm actually solving the continuity equation here in this cell centroid and the momentum equation in this cell centroid, which is staggered to the previous one, which is shifted left to the previous one, then it is called a staggered grid. Okay, so the momentum equation will be solved at this cell centroid. For example, my original cell looks like this. My shifted cell looks like this. So the centroid of the shifted cell actually coincides with the cell face of the previous cell. So this is where the momentum equation is solved, and this is where the continuity equation is solved. So this is basically called the staggered grid concept. So is it clear to you?
Yes, sir.
So how this staggered grid actually came into play? What is the requirement of solving the momentum equation and the continuity equation on different grids? So there's a problem we see. For example, if it's a checkered board kind of an arrangement, okay. For example, the control volumes are there, and if values like 0, 1, 2, 3, sorry, for example, these are the name numbering are 1, 2, 3, 4, 5, and for example, the value of the pressure are basically 100, 0, 100, 0, 100, somewhat like this. Okay, so if I actually take this control volume, so if I actually discretize your momentum equation here, so it will come as AP phi p equals to A phi E plus AW phi W plus some source term. In the Navier-Stokes equation, we already know that the source term will be minus dpdx. Okay, plus rho g. Rho g I am actually ignoring as of now. So this delta V. So first what we do is that we actually multiply the delta V with the source term, and then these are volume integral. So then this control volume is basically equal to minus dp multiplied by dA. Okay, so if area is constant, so minus of dA and P at, so it becomes P at east minus of P at west, this differential area. Okay, is it clear to you? So now we are dealing with this control volume. This P is, the value is 0, at the east surface that is 100, and at the west surface that is 100. Okay, so if I actually reduce it further, it becomes, this is E, this is P, this is W. Okay, so PE plus PP divided by 2 minus of PP plus PW divided by 2. Okay, so PP gets cancelled out, then this becomes P minus PW divided by 2. So we know that at the value at P, P, P and PW both are basically equal to 100. So 100 minus 100 divided by 2, this is equal to 0. Is it clear to you?
Yes, sir.
But there is a problem. We are discretizing the Navier-Stokes equation, but it remains unaffected by the local pressure gradient. 0 to 100 के बीच में एक प्रेशर ग्रेडियंट का इफेक्ट आना चाहिए था, जो नहीं आया, जो इक्वेशन में कैप्चर नहीं हुआ. 100 से 0 में भी होना चाहिए था, because there is a local pressure gradient. Okay, so this is not being captured. So what are the solutions? Don't use central difference scheme. If we actually use some other difference scheme, other discretization scheme, we can avoid this problem, or use staggered grid. So instead of solving at the cell centroid itself, so if I actually solve at the cell face, this point itself, so this becomes 0, this becomes 100. So we need that A, this becomes your cell face of interest. Okay, so this is small e. So A phi equals to AP phi P plus AE, AE phi E. There is a source term. So let us consider it to be like this, minus of dp dx multiplied by delta V, and this becomes like area PE minus P, sorry, PE minus PP. So you don't have to use a central difference formula because we know the value of the pressure at the cell centroid itself. So then this becomes 100 minus 0. So if I use a staggered grid, the effect of the pressure on the Navier-Stokes equation is being captured. But if I use a collocated grid, as shown earlier, the effect was getting cancelled. Okay, and that actually lies the importance of using a staggered grid over a collocated one. So if you don't want to use a staggered grid over a collocated one, then you have to use a central difference scheme. Is it clear to you?
Sir, can you repeat the last sentence, Vishnu?
Now, if we, for example, in the staggered grid, you have seen that the effect of pressure is captured, right?
Yes, sir.
Okay. So what I said that if I use a central difference scheme, then you have to use a staggered grid instead of a collocated one, because staggered is capturing the local pressure, collocated is not. But if you want to use a collocated grid, then you can't use a central difference scheme with a checkerboard distribution of pressure.
Okay, sir. Yes,
Okay.
sir. Fine, sir.
So this actually, uh, this staggered grid, so there are multiple solvers which actually use both the configuration, but that should be backed by logic. So this staggered grid is used in one algorithm which is called the simple algorithm. Semi-implicit pressure linked equations. So where we are going to solve the continuity equation and the momentum equation in a coupled, which is basically d rho dt plus del dot rho e equal to 0, and this ddt of rho e plus del dot rho e mu del square v minus of gradient of p. Is it clear? इस दोनों इक्वेशन को coupled manner में solve करना पड़ेगा, since we are going to get the velocity in the three direction if it's a 3D problem, and we also want to get the pressure. Okay,
Sir, we can't use simple this thing for collocated.
you can use, then you don't use a central difference formula.
Okay, we don't have to use a central difference in if we use
सेंट्रल
collocated.
दो ही सोल्यूशन है, नहीं तो सेंट्रल डिफरेंस मत यूज करो, नहीं
Hmm.
तो स्टैगर्ड बना के यूज करो.
But we can use simple for both staggered and collocated.
हाँ, दोनों के लिए यूज कर सकते हो, बट वही,
Oh.
जब भी स्टैगर्ड के लिए कोड लिखोगे, मतलब तब तब डिस्क्रिटाइजेशन स्कीम काम करेगा, बट कोलोकेटेड के लिए
Hmm.
जब करोगे तब वो सेंट्रल डिफरेंस वाला हटाना पड़ेगा.
Yes.
And this is in a coupled manner because we know that in case of when we are solving the thermal equation, there was one variable and one equations, but as you can see here, there are four variables and four equations. Three momentum equation, because three momentum equation, since you are actually solving the x, y, z direction in the three direction, and one continuity equation. So there are four equations and there are four variables. Uh, UVW
That you're
and
taking rho as constant.
rho is constant. So this one is an incompressible flow. So if you basically have the rho to be a variable one, so then in case of it's a gaseous one, so you can find out the rho from the corporate gas equation, the ideal gas equation itself. But if it's a fluid itself, then you can find out by using the Poisson equation. So those kind of things can be done. So that you have to take into account. Okay. So you have to see how pressure actually varies. But as of now, density varies. As of now, density is constant. Okay. So if density is constant, then your it's an incompressible flow. If density is not constant, it's a compressible flow. And generally, Mach number is less than 0.33, your density variation actually is less than, it becomes less than 5%. So that's actually one of the things you should know. So using Mach number, you can find out that whether it's a compressible or an incompressible flow. Okay. Is it clear to you?
Yes, sir.
Okay. So I hope we can stop as of now. So in tomorrow's class, we will come across this simple algorithm. Okay. And we may do some coding also. Okay. Bye.
Okay, sir. Thank you.
Mm, mm.